Great. I actually did get some questions this morning, so I'm going to go ahead and answer those first before we start dipping into the questions I get in the chat. So, questions regarding the Organic 1 discussion board from last week. You had this molecule, 6. And the question it asked you is, how many chiral centers are there? And of the chiral centers, what is the chirality of each of the centers? And the point of this was to kind of follow up on the lab that we did last week. And I'm seeing a lot of common mistakes with this. The big one being kind of treating this like you can just, well, the big thing is misidentifying chiral centers. I have a lot of students putting down chiral centers that are not chiral centers. So the first thing you need to do is build your molecule. So I've gone ahead and built it in advance. We've got this nice zigzag backbone, and we got both methyl groups coming forward. The next thing you want to do is build your Fischer projection. So we have a CH3 on both ends. I'm going to define the top carbon as the furthest left, and the bottom carbon is the furthest right. We have 4 backbone carbons, 1, 2, 3, 4. And then to build your Fischer projection, you're going to take your carbon chain, and you're going to turn it into a loop. So this way we get this nice this nice circular molecule. And starting with that top molecule, or starting with that top CH3, far left CH3 group, we get, sorry, rotated it. We end up getting group on the left, CH3 on the left, hydrogen. Our other methyl group is on the right, CH3, H. As we move to the next one down, we get the methyl group on the left, CH3, H. There's 2 hydrogens for that one. And this was intentional to make it a bit easier when you do the Fischer projections, which you had to do at the top anyway. It made it a little bit easier to figure out which end of the molecule is which. Now, what constitutes a chiral center? And the fair warning I gave all of you is that just because you see stereo bonding does not mean that center is chiral. Now, if you have a chiral center and we're doing an absolute configuration, meaning we need to designate whether we're doing the R or the S, you will see a wedge. But again, having a wedge does not mean that center, wedge or dash does not necessarily mean that that center has chirality. And the example of this is the second carbon here. So we've got carbon 1, 2, 3, 4, 5, 6. And if we look at this carbon, to be chiral, it has to meet 2 stipulations. First of all, it has to have 4 things bound to it, and we clearly see that in the Fischer projection. And the second is that all 4 groups have to be different. So if we look, we got a CH3, so this is not a chiral center, it's an achiral center. So now we go to the next one. We have a CH3 and an H, those are different. We have a carbon bound to an H and a CH3, well that's true here, but this has a CH3 group and this doesn't. So this ends up being a chiral center. And the same thing's true of this one. When we work through it, we have an H, a CH3, we have a carbon bound to 2 hydrogens and a carbon bound to a methyl and an H, so those 2 are definitely chiral centers. So how do you determine the chirality of that given carbon? Well, the first thing we need to do is assign priorities to each group. So I'm going to start with the second carbon here. Now hydrogen is the lightest, so we're going to follow the Kahn-Ingold-Prelog rules. Hydrogen is the lightest, so we're going to assign that a priority of 4, it's the lowest. And bound to each of these is a carbon. So we've got a carbon here, and a carbon here. Now, all the carbons weigh the same. So we can't say that any carbon is particularly more important than the other. So what we need to do is we need to look at what those carbons are bound to. So this carbon is bound to 3 hydrogens. This carbon is bound to a carbon, and a hydrogen. And this carbon is bound to a carbon, and a hydrogen. So since we look at the first point of difference, the first point of difference here is carbon-hydrogen. So since this has the lower atomic weight bound to it first, this becomes priority number 3. Now, a shortcut if you're dealing with pure alkanes, the longer chain is going to take the higher priority. If we start dealing with heteroatoms, like we're going to start doing with alkyl halides and alcohols, you're not going to be able to use that trick. You're actually going to have to keep counting down. But if we look at what's successively further bonded out, this carbon is bound to a carbon, this carbon is not, this carbon is not. So this makes this the number 2 priority, and this, it makes it the number 1 priority. This makes it the number 2 priority. So now, if we take our molecule So loop it back into our Fischer projection. And we rotate it so this way this lowest priority is back. We've got priority 1, priority 2, and priority 3. And since we have a counterclockwise rotation, this ends up being S symmetry. Now if you do the same thing with this carbon, hydrogen's the lowest, methyl's the second lowest, this will be the highest, this will be the second highest. When we rotate that again, we see that shift in priorities. 1, 2, 3, it's a counterclockwise rotation. So that ends up being S symmetry. So that's how you do the discussion board questions concerning, for organic 1, that staggered backbone. Now, just a fair warning to people who aren't doing the discussion boards, that is your attendance for the week. So if you're not doing the discussion boards, you're considered absent. So if you miss 3 discussion boards, you're withdrawn from the course for lack of attendance. So while I have said you can go back and you can redo the grades for your discussion boards, that is true. If you haven't done them, I would highly encourage you to go back and do them for both the practice as well as for the grade, because it is going to count towards your grade in the course. But if you're going to wait until the test to do all of them, you're going to get withdrawn from the course because you've missed so many class weeks. You can't retroactively make up the attendance. So you have to do the discussion boards that week. Even if it's just putting something down saying, I'm putting down something so I can get my attendance, that's fine. But if you don't answer 3 discussion boards, you get withdrawn from the course. So go ahead and get those discussion boards done. Now, another question I got asked on via the email is about optical activity and enantiomeric purity. And this is actually starting to get into the material that we're going to be talking about over the next couple weeks. The EE, the enantiomeric purity, and NMR and IR and mass spec, all of these are going to start showing up, but we're going to talk about them just in terms of simple problems, in terms of understanding the techniques. So what is optical activity? Well, if we have any given light source, a photon of light is composed of electronic and magnetic components that operate at 90 degrees to each other. But they do have an up-down, left-right orientation. So there's actually an orientation associated with these oscillations in XYZ space. Now, typically, light coming out of any light source is not polarized, meaning that if we looked at just the electronic component, it would be randomly scattered around the z-axis. So what happens for polarimetry is first we pass it through a polarizing filter. So if you have polarized sunglasses, this is what it's doing. It's orienting the light so this way only the up-down oscillations are allowed to pass through. So whereas before it hits the filter, it's randomly scattered around the z-axis. When it comes out, it's purely, the electronic component's purely going up and down. Now, electrons interact with this electronic component of light, and what they will do is they will bend it. So if we had polarized light and hits electron, it will bend it. Now, any given electron has a 50-50 chance of which way it will bend it. So generally speaking, when electrons see light, they are bending it, but they're bending it back and forth with equal probabilities and equal amounts, so this way the polarized light isn't affected. But if we have a chiral molecule, this fact that there is a mirror image means that there's a biasing towards one direction or the other. So when it hits a chiral molecule, the light will actually rotate, and this is where we get the optical activity. There is a net effect on the polarization of the light, and we can measure that deflection. And that deflection is the optical activity. So how do we use this? Well, there is a formula in the notes, and it is that the measured angle, alpha, equals the reference times the path length in centimeters times the concentration in grams per milliliter, or grams per centimeter cubed, times the EE over 100. Now, this 100 here is actually because EE is in percent. So we don't, this kind of shortcuts you from like making the mistake of forgetting to divide by 100. But EE here is defined as the percent of enantiomer 1, so the R or the S, minus the percent of the other enantiomer. And we have the relationship that the percentage of R plus the percentage of S equals 100%. So if we have what's called a racemic mixture, a 50-50 mixture of both the R and the S chirality, the EE here is 0 and our optical activity is 0. So what that means is that one form, the R or the S, will bend it one way, the other form will bend it the other way. Since they're both there, they're both going to bend them equally, and we end up getting canceling out. It's only we have more of one enantiomer over the other do we actually see a net change in the direction. So this is where your EE comes from. Now, you'll see in the notes it says alpha D. The D here is the dextrorotatory. So dextro means it rotates it clockwise. Levorotatory L means it rotates it the other way, counterclockwise. Now, we use the alpha D when we have more of the D enantiomer. We use the alpha L when we have more of the L enantiomer, but basically what ends up happening is that you would get a alpha L and alpha D are related by a negative sign. They're just opposite directions. So in that case, it'll still work out. You'll just end up getting a negative EE, which will account for the fact that you've gone backwards. But anyway, to solve these types of problems, you have to be given so much information. So typically, you're usually given the path length L. There is a formula that works in decimeters. I cannot stand that formula. I don't use it. Everyone works in centimeters now, so just use L in terms of centimeters and use the formula I've given you. And it's actually in the book too. You're usually given grams and the amount of volume that they're dissolved in. And this is a physical constant, so this would be something that would have to be given to you. Or if you're given the optical rotation, you could solve for it. But basically, with a lot of these optical rotation problems, it's kind of more of a plug and chug problem. If you want to figure out the EE, you have to be given the alpha sub D, the L, and a way to figure out the C, and then you would just solve for EE, and that would give a percentage. If you're being asked to solve for alpha, you'd have to be given the EE, the enantiomer purity, and then plug everything in. So that's really kind of the gist of optical activity. Conceptually, it's a harder thing to understand, but in practice, it's very easy to work with. All right, let me make sure that's the end of the email questions. All right, now to the chat board question. You can go over study packet 17 and 18, specifically the indicated bond arrow placement, how to translate to a Newman projection. Yes, I can. I just need to download that really quick. So let's start with the problems on page 17 in the packets. And if you give me just a minute, I'll share the desktop with you so you can see it. So these problems in the course packs, they're not required. They're there just to provide you with additional practice. So we've got this molecule, and I'm going to leave off the hydrogens on my board just to make it a little bit easier to see what's going on. Actually, no, let's leave that. So give me just a minute to draw it in. Oops, flip it around. All right, so let's talk about how we do this problem. So again, this is an organic 1 problem. We're talking about the Fischer projection, and it's indicating that you want to look along this bond. So this is your first carbon, this is your second carbon, and with your Newman projections, you're always going to start with a circle, with your circle representing the front carbon. Now, any solid lines are going to be up, down, vertical in the Newman projection. So in this case, if we look at it, if I'm going to look up in that direction, I'm going to have the CH3 F group coming up. And if you rotate this, so you turn it out of the board, your CH3 group here goes down to the left, and your H group goes to the right. So the question is, what does the back carbon look like? And since the H is solid, it's going to be vertical, up or down. And since we see it opposite this carbon group here, it's going to go down, not up. Anything that has a wedge is going to be on the same side of the Fischer projection. Anything that has a dash is going to be on the same side of the Fischer projection. So since the CH3 here is wedged, it's going to go on the same side as this CH3 group, so we get this. And the hydrogen is going to go on the right. So this is how we get the Fischer projection. Now it also asks you, it wants you to identify the relationship of the two groups that are identified. So in this problem, it's identifying both methyl groups, CH3s, and it wants to know what their relationship is to each other. So since they vary by 60 degrees, this makes the methyl groups gauche. Now, the problem beneath it, which you can go back in the video and see, basically rotates this carbon bond so that now this H group is going up, CH3 is over, and our H is down. So it's taken the back bond and it's basically rotated 180 degrees. How does this change our Newman projection? Well, the front hasn't changed. So if we're still looking from this bond to this bond, nothing is rotated here. But the H here is now up, so it's going to be a solid line, and it's on the same side as this group up front, so we're actually going to get this eclipse conformation. CH3s are still going to be on the same side because they're both wedges, and our hydrogens are still going to be on the same side. So in this projection, these two groups are eclipsed. So this is how you would translate those problems you see on page 17 and 18 into actual Newman projections. Again, anything that's a solid line, that's going to be up and down in your Newman projection. Anything that is wedged is going to be on the same side of the projection. Anything that is dashed is going to be on the same side of the projection. And when you see the solid lines, because use the solid lines to kind of orient you in the Fischer projection, if they form a C shape, they're going to be eclipsed. If they form the Z shape, the staggered shape, they're going to be on opposite sides. Number 4 and number 8 in the lab. Actually, the question of that, is it best to use the Fischer projection for chiral centers? Yes. That's why we developed the Fischer projection, so that we could address issues of chiral centers. So number 4 and number 8 in the lab. So I'm going to need to bring up the lab manual. Yes, so it's basically saying with the arrow, if you're looking in that direction, looking along that bond, the back of the arrow is the front carbon and the tip is the back carbon. Just one more question, then I'll get to you, Nicole. Like your mom. So number 4. So number 4 in the lab manual is asking you to draw the Fischer projection of this molecule. Now, admittedly, this is not a very good question because of the way the lab manual has written this formula. So the formula is HO, CH2, CH, OH, CH2, CH3. So why is this a bad way to write this? Well, it is implied here that this is an ether, and it's not. It's actually an OH group hanging off of it. Now, we can build the molecule using the O as part of the backbone. So we have OH, an alcohol, carbon, 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 carbon. So there's our OH, and we're going to do a squiggly line here to indicate that we haven't had a specified chirality. Now, these two groups here are not chiral. Because this is a CH2 and an oxygen doesn't have 4 bonds, so it doesn't end up being chiral. So we can actually simplify this to be CH2OH look more like this. So how do we draw this Fischer projection? Well, same as we've drawn any of them. We have our N groups, CH2OH, CH3, and we've got our 2 backbones. This being a methylene group, CH2. Now, it's asking you to draw both the R and S projections. So, arbitrarily pick one to start with. So, let's start with the wedge. So, if we do the wedge, our OH will be on the left, hydrogen will be on the right. And the question is this R or S? Because once we know the other enantiomer, it's just this enantiomer with this group flipped. And in terms of the actual stereo drawing, we just switch the wedge to a dash. So the challenge with this problem is actually identifying which of these two is the R and the S. Now, it's pretty straightforward. 4th lowest priority, highest priority. Each are bound to a carbon. This carbon is bound to an oxygen, a hydrogen, and a hydrogen. This carbon is bound to a carbon, a hydrogen, hydrogen. So the first point of difference, this one has the higher atomic weight, O versus C. So this ends up being 2, and this ends up being 3. And if you rotate it, this ends up being counterclockwise. So this is going to be your S conformation, and this is going to be your R conformation. As for number 8, it's actually just kind of an exercise in picking up on patterns. Number 8 in the lab manual is asking you if you have a molecule that has chirality R, 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 so 4 R's. This indicates that there are 4 chiral centers, and in the molecule it's given you the C with the CH2, CHOH, CH3 taken 4 times. You can build a Fischer projection, it gets unwieldy, but the point here is that there are 4 chiral centers. So with those 4 chiral centers, the question is basically what are all the possibilities? So we have RRR, and then we have alternating versions of S. So for each chiral center, there's 4 here. There's 2 to the n possibilities. So there's 2 to the 4th possibilities. So that's 2, 4, 8, 16 combinations. And it wants you to indicate enantiomers and diastereomers. Well, our definition of an enantiomer is anything that has all the chiralities flipped. So the enantiomer of this one is S, S, S. So that's 2. Another option is we can just start flipping signs. So R, S, R, R. And the enantiomer here is R, S, S, S. And we're just going to keep changing the first one and defining the enantiomer. And ultimately, you will end up with 8 blocks, each pair being an enantiomer. So 8 pairs. Everything else between boxes is a diastereomer. So this is a diastereomer of this is a diastereomer of this, and this is a diastereomer of this. Because the definition of our diastereomer is anything where you've changed at least 1 chiral center, but not all of them. So in this case, we've changed 1 chiral center between here and here. The first one is R and S, but the rest of them aren't S's. Here, we've changed 3 of the chiral centers. So we changed that one, and that one, but we haven't changed all of them, which keeps it from being an enantiomer. So that's all 8 is really asking you to do. All right, so Nicole has asked, on the discussion board about aromatic compounds, I don't see what the other 2 conjugate, what are the other two conjugated compounds? and A, B, D, and F were identified, F and 6G. And she's asking if F and G were. So let me bring up that discussion board question. Oh, score. I already have it up. Let me share the desktop with you. So in this discussion board, it asks you four questions. And it starts, the idea of the questions is to get you to understand which compounds are aromatic. So to be aromatic, there are 3 conditions we have to meet. The molecule has to be cyclic, it has to have a conjugated pi system, and it has to have 4n plus 2 electrons in that pi system. Now the issue with saying pi system is that it's kind of misleading. It is true we can involve pi bonds with this, so our double bond here. But we can also include any lone pairs and any cations or anions. So in the case of molecule B, we can include that plus charge on the carbon because that's just a vacant p orbital. The only rule here to make things conjugated is that we have to have the option of a lone pair or we're going to do carbocations because they come up most commonly, but basically a positive ion, a negative ion, or a lone pair to participate in the system. So bring it back to my screen. Bring it back to me really quick. So in that image, A, B, D, E, and F all meet this criteria. A meets it because, bring it back up. A meets it because we have a whole bunch of double bonds that are conjugated. B meets it because there's a lone pair of nitrogen and there's a carbocation, so that can participate. We have the 2 double bonds, so we get a loop. D meets it because we've got the carbanion and the 2 double bonds all adjacent. E meets it because we have the carbanion and the 2 double bonds are adjacent. F is also going to meet this criteria because the oxygens contain lone pairs on them. So we have the 2 double bonds and we have an oxygen that can use one of its lone pairs and one oxygen here to use one of its lone pairs. So in this sense, F is also conjugated because it has lone pairs on those bridging atoms. G is the same way. Nitrogen has lone pairs, so it can participate. I is not conjugated, and J is definitely not conjugated. But G I would not say is conjugated, mostly because those p orbitals on those 2 terminal alkene groups yeah, that does answer your question though. Hey, you're welcome, Lauren. So, but yeah, to summarize, the reason why I and F and G are both conjugated is that there are lone pairs on them, both the oxygens and the nitrogen. So if you have a lone pair, that can also be involved in the pi system as well. Now, only one lone pair can do it, so when it comes to counting your electrons, you can't count both the lone pairs if you need to. You can only count one of them. The other thing is that you have to count them. So for aromatic systems, any atoms that are involved in making your cyclic conjugated system, they have to participate in order to make it conjugated. The nitrogen does have an H to it, but that H is part of the 3rd bond. So for simplicity, we generally just leave the bond off. But really, if we were doing the full line bond drawing, we'd put the bond in there. Nitrogen is 3 bonds plus a lone pair. So we've got 1, 2, 3 bonds and your lone pair. The exception being if we have 2 double bonds coming off the nitrogen, so something like an NO2 group. In that case, the nitrogen looks like that. It doesn't have lone pairs. But if you have nitrogen with an H bound to it, that still counts as a bond. Now, if we had NH2 plus, the plus here would get rid of the lone pair on the nitrogen. But yeah, the H only removes the lone pair on nitrogen if you see that plus charge associated with it, because that plus comes from the nitrogen using its lone pair to act as a Lewis base onto the hydrogen. I think when I said I was just kind of prattling. I is not conjugated. The reason being is that those double bonds are actually going in the wrong direction. So the conjugation, if you're going to use the double bonds as part of your conjugated system, they have to be part of that loop. They can't be bridging off of it. And it's more practically, more of just kind of a physical thing. If they're not in a loop, then they can't. The idea here with the aromaticity is that you're giving electrons free reign to go around this ring. But if you think about it, it's trying to like stir a bucket, but there's like two pipes coming off of it. The water at the end of those pipes isn't going anywhere. Well, that's the point of aromaticity. So any double bonds you use have to be part of the ring you're working with. They can't be attached to it. They actually have to be part of it. Pictures of your models. So this is for Organic 1. For the lab that you're submitting this week, I need pictures of your work. I don't need pictures of the modeling kit, but yes, I definitely need pictures of your work submitted. And they need to be submitted by the start of lab. So if your lab's at 8 a.m., they're due at 8 a.m. If your lab's at 2 p.m., they're due at 2 p.m. And what I'm going to do later this week, well, I'm going to do it after your labs are over, or after you come to lab, is I'm going to release my solution set. So you'll be able to see what the answers are. But obviously I'm not going to release them right now because I don't want like everyone just copying down my answers. You're welcome, Nicole. Now the other thing to keep in mind when you look at the key for Organic 1, there are Hayworth projections. You weren't obligated to do those. I did those because my first semester teaching this class last semester, it said Hayworth. And so I built them so students would have the Hayworth projections on them. But they're definitely not supposed to be there. So don't freak out when you see a whole bunch of Hayworth projections. You weren't responsible for that. And there are a lot of Hayworth projections. Yeah, you're welcome. Other questions? You guys had good questions today. For the Orgo 1 folks, we are definitely done with stereo projections. So if you're like, oh, that was a lot, how much more? This is kind of it for stereo projections. You're on good footing now. If you can do the Fischer projections and the Newman projections and you can draw them, you're in good footing, especially when we start talking about alkanes in the next test. Now we're going to focus on characterization. Characterization is going to be a harder concept in the sense that we're going to talk about a lot of concepts that you were introduced to in Chemistry 1 and 2, but not really like at the level we're going to have to talk about. And again, I'm going to talk about NMR. NMR is the hardest to understand, particularly proton NMR, 1H NMR. Mass spec, the technique, how it's done is complicated. The results are very straightforward. IR, or Fourier transfer, IR, FTIR. The theory is complicated. The application is very simple. And we're going to see this with a lot of these. Polarimetry is the same way. The theory is complicated. The application is very easy. The other one, I think we talked about hydrogen uptake as well, which is something I'm trying to get out of the curriculum because like nobody does hydrogen uptake. It's super dangerous and super unreliable. Because I used to do similar techniques to hydrogen uptake. But again, with a lot of this characterization, you're going to see a lot of theory. Don't let that intimidate you. I want you to understand the theory because from my experience, if you understand the theory of how these techniques, it kind of makes sense why the spectrum looks the way it does and does what it does. So what I don't want you getting into the habit of these techniques is trying to take shortcuts and going, because unfortunately that's what your book teaches. It teaches shortcuts. It's like, oh, if you see this, it's an alkyl. If you see this, it's a methyl. If you see this, it's a terabutyl. That's not helpful. But if you understand where the theory is coming from, then you understand the shortcuts, and you're not so dependent on the shortcuts for the analysis, and you're not completely like left in the dark if you see something that doesn't involve any of your shortcuts. And again, with the theory, it's going to be intense, but the questions aren't going to be that hard because you're just learning the theory and how to apply it. We're going to start bringing this together with the alkanes. We're going to throw in naming and characterization and understanding the energy. So yes, it is a lot to ingest, but we're not going to go hardcore on the application until the next test. And by that point, you should be on good footing. All right, if I'm not seeing any other questions, I'm just going to kind of screw around on my banjo for a little while. But yeah, please feel free to ask questions at any time. I'll definitely put it down and help you out. When you stop hearing the banjo, you'll know somebody asked a question, or you'll know that you've left garner. So close. I need to trim my fingernails. Sorry, false alarm. Unrelated email. So we seem to be kind of out of people watching the live stream at this point. So again, if you ever have questions, please feel free to email me. Again, the live streams are a great way to get your questions worked in person. Keep up with the discussion boards. They are due every week. There is a new one posted every week. And you'll get an announcement each week letting you know what we're kind of covering that week for materials. Other than that, I will see you all in lab this week. Thanks for those of you who were able to show up today, and thanks to those of you who submitted questions online.